Hey folks, all right, well this is the point where we really start to look at how things work behind the scenes, under the hood, if we can see how our programs are actually behaving at, well, nearly a hardware level. There's kind of a virtual layer in there that we'll kind of ignore for the moment, but we want to get a little deeper into how memory is handled in a computer program. So I want to play with a whole bunch of things here, and we're going to get into the topic of pointers, which is a particularly interesting one. All right, so when we compile a program, right, the compiler reads the source code, this .cpp file, and it produces an executable. And that executable has all of the binary machine code instructions to actually carry out whatever the program's supposed to do. So that file is sitting somewhere in the file system, right? Somewhere on a hard drive or whatever it might be. When we run that program, that executable code gets copied into the computer's memory, into RAM, where essentially that, if you like, RAM is our working storage for as something is executing. So the actual code to run gets copied into memory someplace, and space gets set up in memory for all of the global variables and global constants that your program's going to use. Then, as soon as it starts up your main routine, space is also set up for the local variables and the local constants in the main routine. So now we've got memory with a chunk of actual code and a chunk of space for the variables and constants that the program is working on. As each function gets called, more space gets set aside for that function's local variables and local constants. And as the function completes, the space for that function gets freed up again so that it can be reused the next time somebody calls a function. So in memory, somewhere, there's all this space getting allocated for whatever functions are currently running, for the variables and the constants that are part of that function. So this space in memory is kind of growing and shrinking as we make function calls and these function calls complete. So in C++, we can actually explore that memory space, and we can look at particular locations in memory to see what's there or to alter what's there. And the way we do it is by accessing memory through addresses. So every single location in memory has its own unique address. So these addresses start at 1 and just go up to, however many gigabytes of memory you happen to have. So there's just a ton of different memory addresses, all kind of stored sequentially, each one typically big enough to hold just 1 byte, like 1 character of data, 8 bits worth of data. So you've got this massive collection of memory, and we can look at any individual spot inside it to see what's there. So what we're going to do now is explore that a little bit. Again, every variable, every constant in our program is stored someplace in memory. Now, different kinds of data require different amounts of storage. So a char or a bool, they're tiny, we can get away with just 1 byte. An int or a float takes a little bit more space, 4 bytes for them on our system. If we want to store a long or a double, it's 8 bytes. So these different things take up different amounts of memory. And again, that memory is divided into tiny storage locations. So every one of these items that we've got stored kind of begins at some spot in memory. It begins at address 1000 and takes up 8 bytes. Or it begins at address 26,012 and takes up 4 bytes, or something along those lines. So they all have an address where they start, and then they take up so many bytes of memory. And again, there might be this huge range of memory addresses. They start at 1 and just go up from there to however many bytes you can hold in your system's memory, actually in the virtual memory. Now, again, when we talk about the address of a variable, I'm going to be talking about the location where that variable's storage begins in memory. Now, typically, we're going to express memory addresses in hexadecimal notation. So this is base 16 instead of base 10. So the idea is that it's easier to express the way things are aligned in memory if we're using a system that's based in powers of 2. So you do wind up having to get used to working in hexadecimal, base 16. So the idea is a single digit in base 16 can hold anything from 0 to 15. So the way it's done is 0 to 9 represent the same values as they do in a decimal system, right? 0 through 9. But then the characters we'll use for 10, 11, 12, 13, 14, and 15 are A, B, C, D, E, and F. So A represents 10, B represents 11, C represents 12, da 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 da, 15 represents F. So the digits in a hexadecimal representation are 0 through F. So again, we wind up getting used to working in powers of 16 a bit. If you've got a number written in decimal, 537 or something like that, it's 5 times 100, 3 times 10, 7 times 1, right? So it's 5 times 10 to the power of 2, 3 times 10 to the power of 1, 7 times 10 to the power of 0. So in base 16, we're just changing the base from 10 to 16. So if I represent, 530, if I had 537 written in hex, that would be representing 5 times 16 squared, so 5 times 256, plus 3 times 16, plus 7 times 1. So again, it's you do have to get used to the representation. We aren't going to be doing very much in the way of base 16 math at all. I just want you to be aware of what it represents, because we're going to be looking at addresses where it's going to be shown in this base. So again, something like 123 in base 16 in hexadecimal is the 1 times 16 squared plus 2 times 16 plus 3 times 1. So whatever, 291 in decimal if you like. And again, if we're looking at memory addresses in hex, they can look like this, 2B, 3F, that kind of thing, where again, it's 2 times 16 cubed plus 3 times 11 times 16 squared, right? B is 11 plus 3 times 16 plus 15. So again, you can go through and do the math and work out specifically what the equivalent would be in decimal. I'm not going to worry too much about that, but just be aware that this is what the conversion actually looks like. Now, when we write numbers in hex, we need to be able to tell that, if I see something like a 537, I need to know whether they mean 537 in decimal or 537 in hex. So we've already seen that when we write numbers in our programs, they're just in decimal. So if you write things normally, it's in decimal. If we want to show a value in hex, we put a 0x in front of it. And the x kind of short for hex. So 0x and then something means that the rest of that is a hexadecimal value. All right, just so you're aware, when we look at memory addresses in just a second, this is the format that they're going to be written in. 0x and then some sequence of hexadecimal digits. All right. For any given data type, we can figure out how much storage space it needs. We can actually look it up in our code. So there's a size of operator, and you give it a data type, and it tells you how many bytes are needed to store that kind of data. So if I say size of char, it's going to come back with a 1. Size of int, it's going to come back with a 4. It takes 4 bytes. Size of double comes back with an 8. Needs 8 bytes to store one of those. So if you're curious about how much space something takes up, you pass the data type to size of. Now, as we want to start exploring memory a little bit, we can actually look at the memory address of any variable or constant or lots of other things, a parameter. So let's say I've got some variable I, and I want to know where I is actually stored in memory. So you use the ampersand and I, and that refers to that thing's memory address, where I is stored in memory right now. So if we try this on our system, then you're going to come up with an address that looks something like this. Some in hexadecimal, some giant memory address. And again, just because virtual memory's got this huge range of space that it can support. So this is, in the massive memory system we've got, this is the memory address where I starts. And if I is an int here, it's probably taking up 4 bytes. So it's taking up the bytes at blah 80, 81, 82, and 83. All right, now if we can look up memory addresses, we can store memory addresses. So I could look up the address of I and then store it in another variable someplace. So I've got this variable that's keeping track of where I is located in memory. We refer to variables like this as pointers because they're pointing at some other variable. They're pointing at some location in memory. Right? They're kind of pointing to wherever I is stored. So again, informally they're referred to as pointers. And they're just used as ways to remember something else's memory address. Now, for a pointer in C++, we'll also have it remember what kind of information is at that location. So is it a pointer to an int? Is it a pointer to a float? Is it a pointer to a string? All right, it's a pointer to some kind of data that begins at this spot in memory. So when we create pointer variables, we'll specify what kind of data they're pointing at, and we'll wind up sticking a memory address in the variable itself. Now, the way you designate something's a pointer is you throw the asterisk after the data type. So int star or float star or pointer star. So if I've got my regular old integer variable x, I stick 10 in it, and then I decide I want something that can keep track of where x is in memory. So I'm going to create a pointer variable. So I'm going to create an int star, and the syntax is pretty flexible here. You can put the star after the int or the star right before the variable. So int star iPointer means that iPointer is one of these pointer variables. iPointer is going to hold a memory address, and we can tell it to look at any place in memory. But in particular, what I'm going to do right now is say, well, let's figure out where x is and store x's address in iPointer. So again, we use that &x to look up the address of x and store that in iPointer. So if we were using the memory address from the previous screen here, if x happened to be at this location in memory, that's the value that would be stored in my pointer variable. Right? So it's got some big weird value that is just the location of x in memory. So now we've got our actual variable somewhere in memory and another variable that's keeping track of where it is. And ultimately we'll be able to get at the contents of x either through x itself or through this pointer. Say something like, look, go to memory where this thing points and do something with the data there. So we can use the star to declare a pointer, and we can also use that star to figure out what's in memory at that pointer's location. So it's called dereferencing. So if we take our same example as before, where we set up our integer variable x, and we look up the address of x and store that in our pointer variable. So iPointer is pointing to x, if you like. We can actually get at the contents of x through the pointer. So you say star and whatever your pointer variable's name is. So this is saying go to memory where this thing points and stick a 20 there. So this is going into memory at whatever address iPointer is remembering and saying, okay, at that memory location, put a 20. So effectively what this is doing, since that's x's memory address, is we're going into memory and we're wiping out x and replacing its old value with 20. So if we were to see out x now, it would actually display 20. We've changed the value of x through the pointer. Right? So the pointer knows a memory location, and we're saying go to that location, change what's there. So pointers can be fairly powerful, and a lot of the features that we've been using are actually implemented behind the scenes using pointers. Now, we can use pointers the same way as any other kind of variable, right? We can pass them to functions as parameters, right? We can return them as return values. So here, we'll have a variable y, and we're going to have a function that takes a pointer as a parameter. So you pass me a memory address that's supposed to be the address of an int somewhere in memory. And I'm going to get the user to enter an integer, and I'm going to put it in memory wherever that thing says. So you call overwrite, you pass it a memory address, you pass it a pointer to an int, and we're going to replace the value of that int with whatever the user provides us with. So in this case, we have an integer variable y in our main routine. We call the function and we pass it the address of y. We pass it a pointer to y. And so we're saying, okay, well, here's where y is located in memory. And then inside the function, it goes to that location and overwrites it with whatever the user typed in. So now, through this pointer, the function is changing the value of y. So this is a lot like what we've done with pass by reference, right? All of a sudden, I can pass y and let the function change whatever's in y. So what I'm actually doing is passing the address of y and using that to go in and change the contents of y. So behind the scenes, this is what the compiler actually does when you use pass by reference. If you use pass by reference, then when it compiles, the compiler actually changes it to this kind of a notation. So you never see that, but that's the way it's actually doing things. And again, you can do this yourself if you need to. And if you're looking at C++ code that is based on older C code, this is the way you'll see things done. Now, again, you've already had to do this in places. If you remember with scanf, we had, say I've got some integer variable and I wanted to scanf something into that variable. I'd pass the format string and then I'd pass it the ampersand and the variable that I wanted to be filled in. So again, what you were actually passing was the memory address of the variable, the address of x in this case. So you were passing a pointer to x, and scanf was expecting a pointer to x and using that memory address to go in and change the contents of x. So you have been using this before, and this is why you get that weird ampersand x syntax in your scanfs. So that's what's going on behind the scenes. All right, I want to look at a whole bunch of different bits and pieces on specific data types and how pointers are related to them. So if I've got an array, say I create some array of 10 ints, I can look at the address of any individual element in that array using the same sort of syntax as we've done before. You take the ampersand and then whichever element you want to look at. I want to look at array element 0, array element 1, array element 2. Well, if you try a little bit of experimentation, if you just see out array by itself and you spit out the address of that first element and you spit out the address of array, you'll find all three give you the exact same address. So in fact, your array is really just a pointer to the first element of the array. So behind the scenes, pointers and arrays are very closely related. Right? An array variable is essentially just a pointer to an element, a pointer to the first element in the array, with the minor exception that you can't change where the array points. Right? The pointer variable, you could change what memory address it was referring to. With an array, you can't. But again, this means that arrays are actually pretty much just pointers to the start of the array, pointers to the first element in the array. Now, that also explains why passing an array as a parameter to a function lets the function alter the contents of the array, because what you're really doing when you pass your array is you're passing a pointer to the array contents. So you're telling the function, this is where the array begins. And then the function can go from there and change what's in the first spot, and then in the second spot, and then in the third spot. So if you've got an array, you can really treat it like a pointer. And the other way around, if you've got a pointer, you can treat it like an array. So if you've got a pointer to an integer, you can treat that as if it was a pointer to the first element of an array. So they are somewhat interchangeable, pointers and arrays. And that's a bit of functionality that we'll use fairly shortly. Same idea, we can take a look at structs and look at the fields in a struct and see where they are and see how that relates to memory addresses and pointers. So let's say I create a struct, so we'll call it point, and it's got two ints inside the struct, so an X field and a Y field. We'll go through and create one, and we'll put 10 in X and 20 in Y. So this is just to go and experiment with where this stuff actually gets stored. So I can print out the address of the struct, I can print out the address of the first field, X, and I can print out the address of the second field, Y. And what you'll find is that the address of the struct is pretty much just the address of that first field. So again, you can go through and look up the addresses of different components and see how these things are organized in memory. So if you've got a struct of 50 different fields, you can go in if you want to and look at where each one begins in memory relative to the start of the struct overall, how these things are actually organized. And again, you can pass addresses to any individual field, and since you can pass a pointer to it, you could conceivably pass a pointer to one of the fields as a parameter to a function and let that function change the contents of that particular field. All right, again, we can take the address of nearly anything. You can look up the addresses of constants, of variables, of parameters, and again, you can start exploring how things are organized in memory in a C++ program. You can even take it one step further and take a memory address and say, okay, well, I want to look so many bytes ahead or back in memory and see what's after something or see what's before something. So we can go through and create pointers to our variables, or create pointers to our variables and then look forwards or backwards, or pointers to a parameter and look forward or back from that point. Oh, actually, I think there's a glitch here. I think if we add 8, it's not actually going to add 8 bytes, it's going to add the size of 8 ints to where the pointer is pointing. But we can start doing pointer math to look forward and backward through memory to see what's around the thing we took the address of. So again, this allows you to go through and explore your memory space, see what's stored where. So it gives you an interesting opportunity to see how memory is actually structured. Now, this should be raising little security flags in the back of your mind going, wait a minute, if I can look around and see what else is in memory, isn't that dangerous? It's actually not quite as bad as it sounds. Each program is run in its own virtual memory space, so when you're exploring back and forth, you're actually looking backward and forward in your own program's virtual memory space. So you're not seeing what's there for other programs. So it's not quite as dangerous as it sounds. Although, now that we've got the ability to play with things in memory, we can create some pretty interesting disasters for our own programs. But we'll address those kind of piece by piece as we work with this. All right, in terms of the way memory is actually organized, again, the way the virtual memory or logical memory is actually organized for your program, there'll be some space set aside for kind of administrative housekeeping details so that the operating system can keep track of what's going on. There'll be the space for your actual executable code that got loaded into memory when you started to run the program. There'll be space for the global variables and the global constants that your program is using. And then there'll be space set aside for all of the functions that are running. I mentioned that each time a function is called, we set aside space for its local variables and its local constants, and when functions complete, that space disappears. So that space is in what's called a runtime stack. So it's just this kind of a stack, a pile of what's been allocated for functions right now. The first function that was called, and then the function it called, and then the function it called. And this just grows and shrinks as functions get called and as they return. Then there'll be a big batch of space that currently isn't in use, and so your program can keep making more function calls as long as there's still space available there. And then at the far end of memory, there's another chunk of space set up where we can actually make requests as the program runs. We can have our program say, I would like this many more bytes of memory to treat as some data type. And so you can make these runtime calls, these dynamic calls, to actually request specific amounts of memory. And so the way memory is structured is the runtime stack is kind of growing into the free space. And the requests that you make for new dynamic storage, these specific space requests, is growing into the free space from the other end. And as long as the two of them don't hit in the middle, you've still got some free space to work with, and the program can continue running. If your heap or your runtime stack grow so big that they collide into each other, then you're out of memory, you get a crash. But this is, at sort of an intuitive level, the way the memory is actually structured while your program is running. All right, again, this runtime stack, each call to the function gets memory space for its parameters, its local variables, its local constants. So this is stored in this stack or pile, and each time a function is called, that call gets space, kind of a new pile on the top of the stack for that particular function call. And when that function call completes, that space is released so that it can get reused again later. And so if I've got a bunch of different, say I've got my main routine and an F2 that main calls and then F2 calls F1, the way things would look on this stack is you'd have main space at the bottom, because it was the first one called, and then when F2 gets called, space gets set up on top of that for F2's local variables and F2's parameters, and then when F2 calls F1, space gets set up on top of that for F1's parameters and F1's local variables. And then eventually when F1 returns, F1's space is freed up, and then when F2 returns, F2's space is freed up, and then when main returns, the program ends and its space is cleaned up. But again, as functions are called, they get piled on top of the stack, and the program's just keeping track of where the top of the stack is right now, sort of what functions are in there. So this is, when you hear talk of the runtime stack, this is what people are discussing. And then the flip side was the heap, this dynamic memory that our program can make specific requests for an amount of data and what kind of data is being stored. So pointers come into play here in that when we make a request, the operator that we use to make the request is going to give us back a pointer to wherever that space got allocated in memory. So if we ask for space for 50 ints for an array, then that 50 ints worth of space, so maybe 200 bytes, is going to get set aside someplace, and they're going to tell us, they're going to give us back a pointer to where those 200 bytes start. So in our local variables, the compiler knows how much space to set aside for each of those. So in our local variables, the compiler was able to set up space in that runtime stack for them. But in those cases where we don't know at runtime how big we need, how much space we need, we're going to use this idea of requesting a new amount of space and get back a pointer. We'll store that pointer so that we can use the space later. So this is called dynamic memory allocation, and then when we free it up later, it's called deallocation. And so we're going to spend a fair bit of time going through and playing with this dynamic memory allocation and deallocation and using pointers to get at the space that we've created and to free up the space once we're done with it. So this will be a fairly significant topic as we get in there. All right, I just wanted to have a quick little play with some of our pointers here so we can see how some of this stuff works in practice. So again, just working through from the kind of basics there. Just to have a look at, we'll create a bunch of different variables. So we'll create an integer variable x, and we'll get a pointer to x. So we'll look up the address of x and store it in a pointer. And then we'll go through and we'll print out the value of x, so that should be a 10, and x's memory address, so whatever's in that pointer. And we'll print out how much space it takes up, right, the size of an int. And then we'll do the same thing for a double, y, right? So y will set to 10.0. We'll set up a pointer, so this one, d pointer, can point to a double. And we'll store the address of y in there. And we'll go through and print out y's value and memory address and how much space a double takes up. And so we'll just go ahead and try this with a few different values, right? We'll try it with a string, where we'll put the string 10, right? The characters 0 and 1. And we'll look up the address of that, and we'll look up how much space that takes up. And so once we go through and print out those, we'll try actually changing memory through a pointer. So we'll go back to x's address. Remember, I pointer was pointing at x. And we'll say, wherever I pointer is pointing in memory, put 200 there. And we'll just confirm that x's value has changed here. So we'll put 200 in the memory address and print out x just to see that we really have changed x through its memory address. So let's just give that a quick try. And hey, it actually compiled. So again, here we've got an example where we were printing out x's memory address, the address of that int, its current value, and the fact that it takes up 4 bytes of memory. Right? The address of y, and you can see that they're close addresses. You can see that the first part here is the same for both of them. Right? The blah, 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 74, and then the last couple of digits are a little different. And then the blah, 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 74, and the last couple of digits are a little different. So this is actually telling us that these things are really close together in memory. B8 is going to be 8 bytes off of C0 if you're looking at the hex. And if we add 8 to B8, we're going to hit the 16 value, roll over into B's 11, C's 12. So these things are actually just 8 bytes apart, which makes sense in that we've got 8 bytes for the value of y, so y is actually stored between B8 and C0. All right, so we can see these addresses. We can go through, same thing for a string, right? It's got value 10, that's actually the string 10. We can see its memory address, and again, we can see that it's just a little bit further on in memory here. And we can look at the size of this beast, and it's taking up 32 bytes in memory. I guess we've got Z is stored after, before B in this case, right? Okay. So we can start seeing where these things are stored, how much space they take up. And now we'll go back to that case where we actually try and change x through a pointer. So again, that I pointer had this memory address in it, which was the memory address of x. And we were putting 200 in memory at that location. And so of course, when we print x out, it actually has this new value, right? X has changed from 10 to 200. So we can go through and play with these memory addresses. And again, in terms of looking at some of the different bits and pieces here, let's take a look at, we talked about the relationship between arrays and pointers. So let's go through and create a little array here. So just 10 elements, 10 through 50. And we'll go through and we'll print out array just as a value by itself. We'll print out the address of this array variable, and we'll print out the address of each element. And just to see what these things wind up looking like. Oh, and then we'll go through and we'll pass our array to the fill array function and maybe do a little bit of exploring in there. Inside fill array, so we're taking this parameter r, and we'll print out the address of that and the address of its first element. And we'll see that in fill array, the addresses are actually the same. The address of array and r, or array element 0, and r element 0 are both the same. And again, the notion is we're passing a pointer to the array when we pass the name. So maybe just a quick, quick try with that. So let's compile that beastie. Oopsie. Oh yeah, it's just warning me that I'm not really doing anything useful here. And I've got an unused parameter, right, because I'm not doing anything with it in there. Okay. It's okay, those aren't bits of it that I'm too concerned about. Again, in that main routine, we were printing out the array just as a value, and we're getting a memory address. When we print out it's the address of the variable, again, we're getting the same address. And we print out the address of the first element, we're getting still that same. So the array name really acts as a pointer to that first element. And then again, you can see that this array of ints, we're going up by 4 bytes for each new successive int. So that also tells us that the elements of the array are stored sequentially in memory. So again, we can explore through things a little bit. You can do the same sort of thing with a struct. If we look at the addresses of a struct and of its fields, so here we've got a struct that's got an int and a double and an int. We can look at the addresses of the 3 fields and the address of the struct as a whole. So we'll print out the address of the int, the double, and the int, and just see how that goes. And so we get the address of that first int, the address of the double, and the address of that second int. And again, we can see where these things are arranged in memory. And again, you can see that the address for the struct as a whole is the same as the address for the first field. So you can start seeing how this stuff gets arranged in memory. Maybe one more, let's take a look at two-dimensional arrays, since we had to play with those. So for this one, we'll create a two-dimensional array, so 2 rows, 3 columns, and I'm just going to initialize the first row with 10, 11, 12, and the second row with 20, 21, 22. And we'll go through and print out, for each row and column, we'll print out that element's value and memory address. So we can see how this two-dimensional array is arranged in memory. And see where these things are stored. So we'll print out, row 0, element 0, row 0, element 1, row 0, element 2, and then move on to row 1 and do the same thing there. All right, so as we go through and looking at each element in turn, the 10, 11, 12, 20, 21, 22, we can see that the memory addresses are, again, going up by 4 bytes at a time, right, the size of an int. And so, I guess, the size of an int as we're chewing our way through this. We can see that it stores the elements of the first row sequentially, and then it starts on the second row and stores those sequentially. It's actually called row major order if you're ever interested. So it stores the first row, and then the second row, and then the third row, and then the fourth row. So it stores each row in sequence, and within the row it stores each column in sequence. All right, so we can have a bit of a play with the contents of memory now. And we're going to look at a variety of ways to make use of this over the next few sessions. All right, that was plenty for now. I will leave that there.